Yes. Uh, yes, it's really great. Okay, so the goal of my talk is to give you one link. So this is
Sorry, Dr. Charlene, your voice is not clear.
oh,
So you have
my
to.
voice is not clear.
Now it's okay. Just adjust your mic.
Now it's okay.
Yeah, now it's okay.
Okay.
Yeah, now it's
Okay.
okay.
Okay, I will continue then. Yeah, so this I will do at the end, and this is what one of my master students did in his master thesis in the past year. So I thought it would be nice to show, to the students, especially what one of my master students back home was working on. Okay, so let's go into the normal numbers. So as we know, each number between 0 and 1 can be written in a decimal expansion, which looks like this. So 0 point and then some digits. And this is just shorthand notation for a sum like this. So d1 over 10 plus d2 over 10 squared plus d3 over 10 to the third, etc. So here are some examples. Well, we all know these examples. So the digits you can choose from are from 0 up to 9. And then since we have 10 possible digits, and there is no reason why one of these digits would be more preferable than any others, so they all sort of have the same reasons to appear or the same probability to appear, we can define simply normal numbers. So this motivates this concept of numbers that have each digit appear with equal frequency. So a number is called simply normal if each of these 10 digits appears with frequency 1 over 10. Well, we've already seen some non-examples of this. So can anyone name one number that is not normal, not simply normal in base 10? Yeah, so something that does not satisfy this condition. Yeah, exactly. You keep coming up with 1/9. So this is a favorite number. Yes, exactly. So 1/9 only has the digit 1. So the digit 1 will appear with frequency 1, and all the other digits will appear with frequency 0. So it's not normal. So we saw already 2 examples on the previous slide as well, a half and 1/3. They're also not normal. Can you think of an example of a simply normal number in base 10? So what could you do to get a simply normal number? How can you make sure all digits appear? Exactly. Very good. Yeah. So you put all the digits from 0 to 9, and then you start over from 0 to 9, start over from 0 to 9, etc. So this will be normal in base 10. It's not so difficult to show that this is actually true. So it's not so difficult to find a simply normal number. Okay, so we can, yeah, and then for very many numbers, like pi, so I made pi minus 3 to keep it within 0, 1, but of course the same holds for pi itself. So pi is not It's not known whether pi is simply normal in base 10 or not. So no one knows. This is still an open question. Okay. Oh yeah, it's not even known whether all digits even appear infinitely often in the decimal expansion of pi. So we do not even know whether after some moment in time we will no longer see any sevens anymore. Even this is not known. So we do not know very much. We can strengthen the definition of simple normality a bit by asking that not only each digit appear with the same frequency, but that the same property holds for any block of digits. So if I take a block of k digits, and if each of these blocks appears with frequency 1 over 10 to the k in the decimal expansion of the number x, then this number is called normal in base 10. So this is a bit stronger. So of course, the examples that were the numbers that were non-examples before. So these are still non-examples. So we have very many non-examples, but to find examples, this is a bit more challenging now. So here are some famous examples of numbers that are normal in base 10. So the Champernoun constant. So this puts all the natural numbers in a row as digits. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. So it just puts all the natural numbers in a row. That is normal. It was proven. So Besikovic also found or proved that this number is normal. So can you see what is happening there? Exactly. It's the square of all the integers. So if you put them in a row as all the digits, you also get a normal number. And Copeland-Erdős number. So do you see what's happening here? Exactly. So these are the prime numbers. Unless I made a mistake, it should be prime numbers, but I think it's okay. Yeah, so if you put all the prime numbers in a row, then you can also show that this is a normal number in base 10. Okay, so numbers, except for decimal expansions, you can also express them in other bases. Take, for example, binary expansions. So there the base is 2, and the possible digits we can use are 0 and 1. And then any number between 0 and 1 can be represented in a binary expansion by a series like this. So for example, 1 over 3 is 1 over 2 to the 2, plus 1 over 2 to the 4, plus 1 over 2 to the 6, plus 1 over 2 to the 8, etc. So the binary digits are 0, 1, 0, 1, 0, 1, etc. And 3 over 8 is 3 over 8 is 1 over 4 plus 1 over 8. So the binary expansion of 3 over 8 is 0.011, and then infinitely many zeros. So if we can represent each number in a binary expansion, we can do the same definition of normality for base 2. So we call a number normal in base 2 if for each block of digits of length k, it occurs with frequency 1 over 2 to the k in the binary expansion of x. So we just replaced the 10 by the 2 here. So we only have 2 digits. So any block of length k, we expect it to appear with probability 1 over 2 to the k. And then we can do, so to find a normal number in base 2, we can do a similar thing as we did in base 10. We can construct a Champernoun constant by just taking all the representations of all the natural numbers in base 2 and putting them in a long string of digits. And then by the same arguments as for the decimal case, you can show that this is normal in base 2. And then there's no reason why to stop at 2. We can do this for any integer base. So for any integer n bigger or equal to 2, we can define something which is normal in base n. And that says that for each length k, each digit, or each block of digits, a1 up to ak, occurs with frequency 1 over n to the k in the base n expansion of x. So we have for any n, we have a definition of normality. And then we call a number absolutely normal if it is normal with respect to all integer bases. So this is even stronger property. Yeah, so this is the definition of normal number, or absolutely normal number. And this is what the Borel's theorem is about. So Borel's theorem from 1909 says that in fact, almost all numbers x are absolutely normal. And you see that I stopped putting examples because so of course this number is normal in base 2, and we can construct for each integer n, we can construct something like a Champernowne constant for base n, but if it's normal in base 2, so for this number, it doesn't say anything about whether it's normal in any other base. So to write an example here is not so doable. But despite of that, Borel already showed in 1909 that almost all numbers have this property. So I've been teaching a large portion of this class measure theory over the last week. So of course they understand what almost all means. But let me explain, because of course the first question when you read this is what does the almost all mean in this statement. So I will give a very short explanation of what that is. So we are considering subsets of the real numbers. And we say that a subset of the real number has measure 0 if it has the following property. So for each L, an L you should think of as a small number. So however small we choose a number L, we can always find at most countably many intervals in, such that the set that we are talking about is contained in the union of all these intervals, and the sum of the length of these intervals is less than L. Let's give a simple example. So suppose our x is just a single point 0, and we take any value for L. Here I took some random L. You cannot see whether it's big or small because there's no scale in this picture, so it can be anything. And then what can we do to show that this set, so this is a single point, right? So if we want to think of measure 0, we think of that as a small set. So if we want to measure 0 sets to be our idea of small sets, then this set should have measure 0. Otherwise, we did something wrong in the definition of measure 0. So this set should be a measure 0 set at least. So how can we get these two properties for this set X, for this single point? How do we choose? Yeah, he has a pre-knowledge. He was also there on Wednesday. So how can we choose this in these INs so that these two are satisfied? What can we do? Oh no. Exactly, and the epsilon in this case will be L. Yeah, precisely. Yeah, so if we take for L, so if anyone gives us an L, we just take one interval, which goes from -L/4 to L/4, and then X will be contained in this interval, and the length of that interval will be L/2, so that will be less than L. So this shows that our single point set is measure 0 set. So now suppose that we have a whole interval, the interval from 0 to 1. So can we then do the same thing? Well, if we take any collection of intervals such that this interval is contained within them, then the lengths of all these intervals must sum up to something that is at least 1, right? Because otherwise we cannot cover this one interval. So if we take L less than 1, then we cannot find this collection of intervals such that the lengths sum up to something that's less than L. So an interval is not a measure 0 set for this definition. I'm sorry? Any number bigger than 0, but you should think of it as however small I choose this L, I can still do these two things. And here you can only do this if L is bigger than 1. So if you make L smaller, then you cannot do this construction anymore. Yeah. So any L still works. So how can you choose? Do you have an idea how you can choose the intervals then? So you anything else? No? So suppose we have 2 points. So what do we do then for this definition? How do we choose the intervals I, N? Exactly. Yeah. We take take two of these intervals. Maybe we make them a little bit smaller because we want the length to sum up to something that is less than L. So maybe we put an 8 here or something, and then we can still do the same trick. And in fact, you can do the similar trick for countable sets. Yeah, for rational numbers, it still works. And it's even stranger than that. So this is maybe not strange. Countable set is still pretty thin, right? But you also have measure zero sets that are uncountable. So yeah, so they can still be pretty big, but they have this property here that you can cover them with these intervals. So yes, yeah. Yeah, you can do a similar thing. You have to be very clever in how you choose INs. Yeah. Yeah. So this is what a measure zero set is. So then Bonnell's normal number theorem says that the set of numbers that are not absolutely normal is a measure zero set. So it can still be very big. We know, for example, that all rationals are in there. So it can still be quite big, but it is but the complement is also quite big in the sense that the set of exceptions is just this measure zero set. Okay, so now let's go to dynamical systems and show you. So there are many proofs of Bonnell's normal number theorem, and Bonnell himself, he didn't use dynamical systems, but I would just like to show you how you can get to the proof through dynamical systems theory, just to show you that there's a link between these two fields. So just to illustrate that. So just in very general terms, a dynamical system, that is a model for any process that evolves over time. It's a very general concept. So here I put 3 pictures, and I also put these on Wednesday. And no one has since told me what the name of this place is. So these 2 pictures are from my own phone. This one, unfortunately, not. I would have liked it to be from my own phone, but I've not been there. But it looks like a very pretty place. So, but yeah. So, for example, so this is the north of Pakistan. I guess some of you recognize it. Please tell me the name. For example, water flows or fluid flows, you can think of them as a dynamical system. They evolve over time. So this was taken when we went to visit a museum from the back of the van. So here you see nice old buildings. So traffic flows is also an example of a dynamical system. So this was here last week on the big screen in the building downstairs. So this is the air flows that are depicted here. So I felt very much at home when I walked into the building, and the first thing I saw was this big picture of a dynamical system on the walls. This is a good place to be. So anything's basically a dynamical system, anything that evolves over time. In the simplest case, so of course you can see from these pictures that these can be very complicated systems that are very difficult to describe, and you need a lot of machinery and a lot of theory to understand them well. Fortunately for the goal of this talk, dynamical systems that relate to number systems or number expansions are very easy dynamical systems. So these we can understand and these we can describe very well. And in the simplest setup, a dynamical system consists of 2 ingredients in discrete time. A set X, which is called the state space. So this is the set of all the states that a system can be in, and a map F that maps the state space to itself, and this sort of gives you the time evolution. So in the following sense, so if the system is in state x0 at some moment in time, so let's call that time 0, then it will be in state x1, which is f of x0 after 1 time step, and in x2, which is f of x1, which is f of x0 after 2 time steps, etc. So if we like to consider the whole time evolution of the system, then this is what happens if you start at point x. So you go from x to f of x, f squared of x, f third of x, etc. And this collection here is called the orbit of f under x. So so that's a baby form of dynamical systems. So now let's go back to the number expansions. So they can be generated using this very simple dynamical system. So as our state space, we use the unit interval, And as our map, we use the map 2x mod 1, which looks like this. So it's 2x on the interval from 0 to a half, and it's 2x minus 1 on the interval from a half to 1. And then we can get the binary expansions from the orbits under this system. So we assign a digit 0 to the first half of the interval, and we assign the digit 1 to the second half of the interval, and then we do the following. So for any point x, so suppose we take this point x, so this is 1/3, we look where it is. If it's to the left of a half, we put the first digit equal to 0, and if it's to the right of a half, we put the first digit equal to 1. So for x, d1 is 0. Then we compute f of x. So in this case, it is 2/3, which lies to the right of a half. So we put the second digit equal to 1, and then we continue. So this one is nice because f of x goes back to x. So f squared of x is again 1/3, so we get digit 0. And then if we iterate this, we get 0, 1, 0, 1, 0, 1, 0, 1, which we already saw before. So by just following the orbits, we get an infinite string of digits. And the claim is that these are precisely the binary digits of x. So this is, of course, a claim. So we want to verify this. So we have set the digits up in such a way that we can now write f of x is 2x minus the first digit, because we put it 0 here, and this is 2x, so 2x minus 0, and we put it 1 here, and this is 2x minus 1. So for all x, f of x is 2x minus the first digit. And then f squared of x will be 2 times f of x minus the second digit, etc. So this property holds for all iterates. So now if we look at this thing here, and we isolate x from it, we get this. So we take the d1, we take it to the other side, we divide by 2, then this is what we get. X is equal to d1/2 plus f of x/2. And now we do the same thing with this expression. We take d2 to that side, we divide by 2, and we put that expression in here. Then we get d1/2 plus d2/2 squared plus f²/2 squared. And if we do this n steps, then we get the first portion of the binary expansion of x plus this error term. And since this fn of x stays in this interval all the time, so it moves around, but it's always between 0 and 1, and this power of 2 grows, this will converge to 0, and in the limit you get the binary expansion of the point x. So here you get, you see how the binary expansions pop up from the orbit of this system. So now let's go to some serious dynamical theorems, which is the ergodic theorems. So in around 1870, Boltzmann, who I think is considered as the founding father of statistical mechanics, he had very many ideas about how large systems of interacting particles evolve over time, and in particular about what is written here, time average equals space average. So the hypothesis that I wrote down here, so for large systems of interacting particles in equilibrium, time average equals space average. So this can nowhere be found to be stated like this by Boltzmann. So I think this is just like a summary of his ideas. But I think he never actually thought that this was accurate. And in fact, many years went by and people searched for interpretations of this hypothesis and conditions under which this statement actually holds. And these were found in 1931 by Birkhoff and von Neumann. And they were formulated in the ergodic theorems. So they both have their own version of the ergodic theorem, which makes precise what we mean by time average and what we mean by space average. And they also say under which precise conditions these things are equal. So this is a very general theorem. The time average comes from taking one orbit of the system and evaluating some orbit of the system or some observable on the system along that orbit, and then taking the average value of that. So that's the time average part. And the space average would just be the average value of the observable over the whole system. So usually this is like an integral of an observable over the whole space. So this is the mathematical interpretation of time average and space average. Yeah. Yeah, the distribution of the space. So you wait until it lands in some equilibrium state, yeah, or equilibrium distribution. Yes. Okay, so a special case of Birkhoff's ergodic theorem. So I've completely filled in all the details. So this is like a very special situation is the following. So I took for the state space, I took the unit interval, and then the function or the mechanism that gives you the time evolution has to satisfy suitable conditions. So I do not want to explain precisely what these are. These are quite a bit. But then if you have these two, then for any two numbers a and b in the unit interval, it holds that almost all points, for almost all points, we have this statement. And the statement says, so the top part here, so this counts the number of times that the orbit of x lands in the interval from a to b in the first n steps of the system. So the system evolves. So we have x, then we have f of x, the square root of x, and this just is the number of times that this orbit is inside this interval in the first n time steps. Is that clear? Yeah. And so the number of times. Yeah, so this is a discrete set. So it just counts how many times do I see this point inside this set. Yeah, yeah. So you just follow it. If it's in there, you add one here. Yeah. So you look at the first n times, you divide by n. This means that this is the proportion of the time in the first n time steps in which this point was in the set from A to B. And this is like a time average. So you follow the orbit of x and you record what proportion of time the point spent in this specific interval from A to B. So in the setting of this hypothesis, this will be the time average along the orbit of x. For any interval, so you fix an interval at the start, and then you know that almost all x will have this property. So you fix an interval and then you look at this number of times that the point lies in this interval. Yeah, or the proportion of time actually. And then if we send n to infinity, we get the proportion of time that the orbit spends in the interval over all of time, say. Yeah, and then the conclusion of the Birkhoff ergodic theorem says that this proportion is equal to the length of the interval. So the amount, the proportion of time the orbit spends in a certain interval is equal to the length of the interval. Okay, yeah. So let's go to what this says or tells us about normal numbers. Okay, so I put it here just for us to remember. So it's the same statement. So now go back to the doubling map, and we've defined the digits dn to be 0 precisely if after n minus 1 iterates, the point x is in the interval from 0 to 1. But this is what we did before. Okay, so for each x and each n, if we look at this quantity here, which corresponds to this thing here in the top, so what does this tell you? In terms of so what's the interpretation of this? Yeah. And in terms of, that's precisely right. And in terms of binary digits, this corresponds precisely to we're not there yet, we're getting there, but this will be the next step. So this part will be precisely the number of digits that is equal to 0 in the first n iterates. Yeah. So this top part here counts the number of times that the digit the the digit of x are equal to 0 in the first n steps. So then if we divide by n and we take the limit as n goes to infinity, what we get from the Birkhoff-Ergodic theorem is that this is equal to a half, because the length of this interval is equal to a half, right? So this says that by the Birkhoff-Ergodic theorem, for almost all x, half of the digits are equal to a 0. And then, of course, if all half of the digits are equal to 0, the other half must be a 1. So we have frequency 1 for frequency a half for the digit 0, frequency a half for the digit 1. So this application of the Birkhoff-Ergodic theorem tells us immediately that almost all numbers are simply normal in base 2. Yeah, that's a direct consequence. Okay, so now what about blocks of digits? Yes. Okay, so this is simply normal. So yeah, so now let's consider blocks of 2 digits. Thank you. It's a very natural bridge to the next slide. So we look at blocks. So take for example the block 1, 0. So then we know that x starts with 1, 0 if it looks like this. So it's a half plus 0 over 4, and then some bunch of other digits we don't know. So this actually means that x lies in the interval from a half to 3 over 4. Right? So x starts with the block 1, 0 if and only if it lies here. Well, you can debate about this endpoint here, but let's forget about that for a second. And then the same holds for any n. So the block 1, 0 appears in the nth position of the binary expansion of x, precisely if after n minus 1 iterations, the point x lies in this the same interval. And now we do the same thing. So this number will be the frequency of the block 1, 0 here. So I've replaced the interval from 0 to a half by this interval here. And this has length 1 over 4. So by the ergodic theorem, this gives that almost all x have the block 1, 0 in the binary expansion with frequency 1 over 4. And we can do exactly the same trick for all the other blocks of length 2. And then if we can do it for blocks of length 2, we can do it for any length. So if we have any block from A1 to AK, we can do the same procedure again, and for any of such a block, we get a set x, A1, x up to AK of measure 0 of points for which this block does not appear with the right frequency 1 over 2 to AK. But we have to note, so we have to be a bit careful, we have to note that these sets here, these measure 0 sets that are the exceptional points, these can be different for each block. Right, we do not know what these sets are. So these sets that come, measure 0 sets that come from the Birkhoff-Ergodic theorem, they can be different for each block. So we need to do something there. Right, so each of these sets can be different. But note that if x is not in the union of all of these sets, this means that it will be normal in base 2. So if we take the union of all these measures of sets, then we get the sets of x's that are in the measure 0 set for some of the blocks. So if x is not in this set, this means that any block appears with the right frequency 1 over 2 to the k in the expansion of x. So if x is in the complement of this set, then it will be normal in base 2. And luckily, since there are only countably many blocks, this union will again be a measure 0 set. And that's why almost all numbers are in base 2. So that's the proof for base 2. And then we can do the same thing for any other base. So any base comes with its own dynamical system. So this is the system for base 2, for base 3. This is for base 10. So this is the reason why I chose to do the proof for base 2 instead of base 10, because here we cannot really see anything, too many branches. So for any base, we can find a measure 0 set of points that is not normal with respect to that base. And since we have uncountably many bases, we do the same thing, and we know that almost all numbers are absolutely normal with respect to all of the bases, are normal with respect to all of the bases. Okay, so now we know all of them, or almost all of them, are absolutely normal. But finding them is a different trick. So and then each digit second. And then you can see so the patterns here, they come from the very constructed way in which the Chamfernoun constant is defined. So it's a very highly structured number, so to say. But if you convert it to base 2 and base 6, you see absolutely no patterns whatsoever, which corresponds to the fact that if we know how to write a number in base 10, it tells us very little about what happens in any other base. So it's as I said before, it's not known whether Chamfernoun's constant in base 10 is normal in any of the other bases, but it sort of looks convincing that this might be the case, but we have no proof of that. So 250,000, so this is a number in decimal digits. So they computed 250,000 digits of the binary expansion of this number. So they converted it to a binary expansion. And then they gave digit 0, I don't know which one. Digit 0, they made it green. Digit 1, they made it red. And then they started here and then put all these 250,000 digits in a row, coded by colors. Yeah. Yes. Okay, so are there any constructions known? This is the question. So already in 2017, the Berg and Sierpinski gave constructions of absolutely normal numbers, but they were not computable. So there was no algorithm for them, such that if anyone asks you to compute the nth digit, you can actually compute the nth digit. So no, it exists. There is a construction, but it's not clear how to actually get the digits of these numbers in any base. A little bit later, Turing and also Wolfgang Schmidt, they gave constructions of normal numbers. And then very recently, let me put the quotes, there was quite a lot of improvement. So Becher, so she's the woman from the pictures, these ones. So they found an absolutely normal number or construction that you can compute in a bit more than quadratic time. And they also gave they gave many more digits, but I only put these many on the slide. So it looks like this, but there's no nice expression for them other than the construction. So this is what we have. And then a bit later, they found a construction. So Lutz and Mayer-Domo, they found a construction that is computable even almost linear time. So this is good, but I couldn't find any digits for that. So these are digits in decimal extensions. Yeah, so to find, and of course, yes, this is as good as it gets. These results are quite recent. We do not know much more. So the situation is still very much unknown. Yeah, so as I told before, so I was once approached by a researcher in Warwick in England who asked, so what kind of research do you do? And I said, I do ergodic theory. And then he said, well, we don't even know whether pi is a normal number in any base. It's a disgrace. We should solve this, and you should do this, or people in ergodic. With he meant people in ergodic theory. But yeah, of course, as you saw, ergodic theory only talks about typical numbers or almost all numbers and makes no statements about individual things. So I'm not a suitable person, I guess, to attack this problem, but it's definitely something we would like to know, of course. Okay, so I think I might have too much here. So I'm not sure what I can skip, so let me go through it. So what I then wanted to do was show you what my master student did and look at normal numbers if you have an infinite digit set. So these all had finite digit sets, and then you can have a chamfer noun-like construction. But there are also number systems with infinite digit sets. And one example of this is something that was found by Lumot in 1887. And he describes number expansions that have this form. And the digits di, they can take any natural numbers. And this is the abstract from his original German article. And it says something like, I allow myself to look at this strange representation of numbers between 0 and 1, and that he found this when he looked at functions from manifolds with different dimensions to each other, and he was looking at these functions because he was, I don't know, motivated by some work of Cantor. And then somehow in his research, he found these expansions and he decided these were interesting in their own right. So he started investigating them. And he mainly investigated properties of rational numbers in this system. Okay, so in 1968, Jager and de Vloed, who I think are both Dutch. You don't know de Vloed? Yeah, Jager, I think, is definitely Dutch, but de Vloed, I'm not sure. So they show that you can have a dynamical system that generates these expansions, just very much like we had the binary system. But in this case, we need infinitely many of these branches because we have infinitely many digits. But the procedure is precisely the same. So we assign a digit to each of these intervals, and then we follow orbits, we write down the digits, and then we get these Liouville expansions of this way. So the kth digit or the nth digit is k, precisely if after n-1 iterations, the point is in the interval from 1 over k plus 1 to 1 over k. So this is precisely the same as before. And then you can ask what normality means in this setting. So recall how you got the digits. Also recall Birkhoff's ergodic theorem, which looked like this. So if we now apply Birkhoff's ergodic theorem to this system, then we get that for almost all x, the number of times that this orbit lands in this interval is precisely the length of this interval. So it's 1 over k minus 1 over k plus 1, which is 1 over k times k plus 1. And this says, given we have this definition of the digits, that for almost all x, we expect the digit, oh, there are too many k's here, I see. So it should be I. So we expect the digit k to appear with this probability or this frequency. So for almost all numbers, this is the frequency with which we should see the digit k. So this is the idea behind this definition. So we call a number x Liouville normal if in the Liouville expansion of x, each block of digits occurs with this frequency, which is the product of all these things for the different digits. So the motivation for the normality definition also comes from the dynamical system that underlies it. And then you might wonder, how can you construct such a number? So there are obvious problems here. We cannot do what Chamfernoun did, because if we start concatenating all digits, we run out of place, right? We have infinitely many of them, so this is an obvious issue. And then stemming from that issue is the fact that all these different blocks, they will have different frequencies. So you need to also take into account this fact there. So here are some people who tried different things. So Box he gave a construction in his bachelor thesis even at TU Delft in the Netherlands, but he couldn't finish the proof within the scope or within the time for his bachelor thesis. Van der Heij, he only looked at finitely many digits, so he somehow avoided the problem. He only fixed the problem where you have different probabilities for different blocks. Mareich and Mens, they have an actual construction of a normal number, and it looks like champ-pronounced constant, and it has very many iterations of the same blocks. And just put so many iterations of the same block of digits there that he can then manipulate, or they can then manipulate the frequencies in the way they want to. The advantage of their result is that it works very generally. So for very many different number systems, they can do this. This is a construction of a similar type, but not for the Newland map that I showed you before. And this works through continued fractions. And then with my master student, Afko Boomstra, we managed to find a construction for the Newland map and some generalizations of it by quite elementary setup. I think I'm out of time or not. Can I show the tree? Okay, so this is what we did. So this is actually in the bachelor thesis. It contains this tree. So it sort of runs. So I put the blocks now vertically because otherwise it didn't fit in the slide. So what happens is we start with 1, then we have 1, 1, 2, 1. So if you go to the left, you append a 1 at the end of the, that's here. So if you go to the left, you append a 1, and if you go to the right, you add 1 to the last digit. So this is 2. If we go to the left, it becomes 2, 1, but if you go to the right, it becomes 3. And also here, 1, 3. If you go to the left, it becomes 1, 3, 1. If you go to the right, you change this 3 into a 4. That's how the tree is sort of set up. And now we put probabilities there, which somehow corresponds to the probabilities we saw before. So these 1 over d, d plus 1. So these are all these probabilities. And this was also already in the thesis by Box. And then what we did was walk through this tree and use the weights to determine how often we would put the number there. So yeah, so you put a weight to each node, which is just the product of the probabilities. So each block has a probability, which comes from walking down the tree to that point. And then what we did is we proceed through the tree, and then for each level of the tree, we add n. If the level is n, we add n factorial words from that level, and we distribute them according to their weights. So we multiply the weight with n factorial to determine how many, and then this might not be a natural number, so we round it up or round it down if necessary. And then this was not enough. So I have some examples here, but that might be, let me cut to the point. This was not enough, so we had to add a third condition, which somehow, so this looks horrible, but it says that on any level, we have to somehow reflect what happened 2 levels above. So we cannot just concatenate using these 2 rules, but we have to be a bit more careful. Otherwise, we can have big frequency drops in this sequence, and it might not converge. The frequencies might not be well defined. So we need to add a little bit more complication to get the actual normal numbers. So I think this is only the so this is only starting from level 4. Looks something like this. The rest is on the previous slide. But yeah, so just to show you how the construction works, of course, the proof. Let me not go into that. So let me stop here. In. Yeah, so what we did was, so if you look at the n factorial, we split them into n times n minus 1 groups of n minus 2 factorial words. And then within each of these groups, we have to have a representative of all the words in level n minus 2. So you cannot put all the, so for example, if you look at the words from level n, level 4, these are these words. And what this third condition does, it says that you cannot put them like this, because now you see all the ones are bunched in the front and all the higher digits are here. And if you do it like that, then the frequency can drop too much. So you need to mix them sufficiently. And this this works. We do not know if it's necessary. We suspect maybe this might be too strong, but we cannot find a weaker condition under which this works. So this is sufficient to get enough digits mixed, and you cannot have this bunching of the ones at the front. Yeah. No, this is a construction. So yeah, we just constructed normal numbers. So actually, there's some freedom. You can choose different things. So it's not one; it's a bunch of them. But you cannot use it to verify anything. Now, this is always the hard question, right? If you would have something to verify, that would be gold. We can look at pi and we can look at all the other numbers. Yeah, no, this is one direction. But actually, the setup is a bit more general. So here, in the tree, so these probabilities here, they are very special. They come from the Lirot tree before, but actually we were able to deal with any probabilities here, which then extends this construction to other types of number systems as well, outside of the Lirot map. Thank you so much. Well, personally, I just like them a lot. So I think it's very interesting that we still do not know so much about these simple numbers, but you might want to know whether there are applications or something. Is this? I'd say yes. So one thing I know, but so I'm not an expert on this, but what I know, one thing I know is that this is a cheap way. So normal numbers are a cheap way to simulate randomness. So if people have to use random numbers in, I don't know, in anything, you can get a proper seed and you can, properly set this up to work. And this is sometimes, depending on what you want to do, this is very costly. So it takes a lot of time and a lot of care. And then you can do this, you can take these normal numbers, and then you have something that's not as good as an actual random number, but it's sort of sufficient to test certain things. So I don't think they, to my knowledge, I don't think they use it in actual applications so much, but maybe they use it in phase up to some applications to, speed up the computations and to make things easily manageable. Yeah, I don't know if they're No, there's nothing like that. I think, which is the big issue. Yeah, so there is no good way to transfer properties in one number system to another number system. Well, at least for the base n expansions. I think for other types of number expansions, there might be some relations. So, for example, for continued fractions, certain types of properties you can relate to each other, but in this setting. Not with the base n systems. So there are relations between certain Lirot expansions and continued fractions as well, but these are all through strange, non-singular functions like Minkowski question mark type functions. So yeah, even if you know that this relation exists, still these things are so intangible, it's difficult to get actual statements from them. I'm not sure, but I'm sure many people thought about these relations. Yeah, continued fractions are really nice for this, right? They always work. They always work very well. Yeah, so I'm not aware of any results, but many people have worked on these normal numbers, so I'm sure something is known. But even simple statements, I think are also still not known. So I think it's still open question whether all irrational algebraic numbers are, or yeah, normal, or to what extent. I think people are actively looking into that still. Yeah. I don't think that is necessarily true. So almost all numbers are. Can you get a very easy counterexample? Add two things to get then a rational or something? I don't know if you can find an easy construction. I cannot answer. But probably you can do things. That you say it's not. There's no reason to believe. Wow. Yes, exactly. Yeah. Well, in most cases, oh yes. So this would be in most, but yeah. But I don't know how to go from alpha to alpha over 2 and look at the digits of that in all number systems. So yeah, you can construct probably things, but then you need more information. Yeah. Yes. Yeah. So let me see. Uh, so this is what you're after, right? So you have well, here there's the, I don't know if I have a version with the digits, probably not. So these are the type of limits that you look for. So you want to study the digits and whether or not they are equal to k, or whether the dynamics is in this interval for longer and longer patches. So the way we did this for this infinite one is by chopping it up into pieces where we would know what the result was in that. That was actually also how we found that our first attempt failed. So so we first add up. So we first take all the words of level n, and we make n factorial of them, and then we put them there. And then after you've done that, you have very good understanding of what is in your number. So we found the subsequence where we had good convergence. And then at the beginning we were happy, and then we found that the subsequence was not enough because we could find other subsequences that do not converge to the right frequency. So that's why we had to actually add this third condition to make sure that this subsequence would also behave nicely. Yeah. I'm just checking if there's some question from the audience. So you can ask the audience. Okay. So we have Yes, yeah. Yeah, I avoided a bit. I called it length, but it's the measure. You can ask that. Okay. Did you? So we saw the questions in the chat. Did you? Are they answered, or would you like to know more? I don't hear anything. Okay. This is the case now. Champernowne constant. Yeah. No, it's only normal. So you have different Champernowne constants for each base. And yeah, for each of them, we do not know whether they're absolutely normal. So the picture, the one I showed with the colors, might suggest that maybe it is, but there. there are countably many other bases to check also, and also the pictures are not a proof. They are just some illustration. So different. The idea is the same, but the number is different, right? Because you put the representations of all the integers in the base that you're considering after each other. And this is a different number if you do it in base 10, you get a different number than if you do this in base 2 or in other bases. Yeah. Thank you so much.